Okay, so in this video, let's talk about the hybridization. This is a very small topic and straightforward one. I will explain this by a simple example. Let's say methane, CH4, right? So when this carbon is bonded with 4 hydrogen atoms, right, you have to know the carbon's electron configurations first. So it is 1s2, 2s2 and 2p2. So let's say when the bonds are forming, only the latest energy level matters. This first energy level doesn't interact with the bond, so we will forget it. When it comes to the latest energy level, there are two orbital types, s orbitals and p orbitals. One s orbital, right, and 3 p orbitals. This is p orbitals, 2 p orbitals. This is 2s orbital. So there should be 2 electrons over here and then 1. This is the orbital diagram for carbon in normal matter. So when it bonds with 4 hydrogen atoms like this, 2, 3 and 4, right? Okay, so the experimental data suggests that all these 4 bonds, right, must be equal. That is a fact that has been found using experimental facts. So whatever, these 4 orbitals must be rearranged in order to give 4 equal bonds. So what happens is, in the excited state, this electron configuration rearranges like this. This 2s, 1 electron is moving into p orbitals, 1, 2, 3, 4. Now our main problem is solved, right? As you can see, there are 4 orbitals which can be interacted with another orbitals to form bonds. There are 4 orbitals to form 4 bonds, but there is a problem. When it comes to the energy, you know that this is 2s orbital and this is 2p orbitals. These two are different in energies. The incoming other part is the hydrogen. Hydrogen only contains 1s orbitals. So hydrogen has no effect on this equality manner. It should be carbon. So the scientist suggests that these 4 orbitals rearranges again to become equal 4 orbitals. So I will represent it like this: 1, 2, 3, 4. This is 2s, and here we have a 2p. So this rearranges 1, 2, 3, 4. We call these new orbitals as sp3 orbitals. Why we call that? Because to form these new orbitals, we have involved 3 p orbitals and 1 s orbitals. Here 1 s orbitals and 3 p orbitals. So you need to know that these newly created orbitals must have energy between the 2p orbitals and 2s orbitals, and it should be closer to 2p. Why? It has like 75% of p characteristic. Here total is 4. The total is 4 and 1 is s, 3 is p. So more characteristics from p side, which means it is more like to be p orbitals, but it's not equal to the p orbitals. You need to know that. So here this is the energy, this is the s energy. This should be in the middle, right? It should be at middle, right? This is the main thing about the hybridization. And when you're finding a hybridization using a normal structure, like here in this matter we have CH4. Let me take a color. Right, okay. Here we have CH4. In exams, you must know, when the examiner asks you what hybridization is, this carbon is formed, you need to answer whether it's sp3, sp2, sp likewise. So these three are the most common hybridization we meet in our organic chemistry. So I hope you get the idea, right? In this case, the hybridization forms with 2 p orbitals and 1 s orbital. In this case, we have 1 s orbital and 1 p orbital to form the hybridization. So normally, when bonds form 5 bonds, right? This is a important thing. The 5 bonds won't involve anything to do with hybridization. So if you see any 5 bonds, which means it's a pure p bond. It's a pure p bond. It has not involved in any kind of hybridization. So let's do some examples to determine how to determine the hybridization of several atoms. So let's firstly take this atom CH3, CH3. So we are being asked to determine the hybridization of this carbon. So you need to know is to when determining the hybridization, you need to see about 2 factors. The first thing is how many sigma bonds. How many sigma bonds, right? How many sigma bonds are forming around your atom. And the second thing you need to is how many valence electron pairs. How many valence electron pairs? So let's go around this. So in this case, this is like 1 hydrogen, 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 and here carbon. So first thing, how many sigma bonds? There are 4 sigma bonds. How many valence electrons? There are none valence electrons. So total we have is 4. So you need to get 4 from whether sp3, sp2 or sp. The total orbitals are 4. You need to find whether which combination is coming to form the or coming from 4 orbitals. Here only 2 orbitals, s1 p1, 2 orbitals, 3 orbitals, s1 p2. Here 4 orbitals. So this is the answer. For this carbon is at sp3 hybridization. So let's take another example. Let's take carbon dioxide. This is the carbon dioxide structure, right? This is carbon dioxide. Okay, so what is the hybridization of this oxygen and carbon? So as I know, you need to know about the Lewis structure, right? You need to know about the Lewis structure. So in the Lewis structure, there are no valence electrons on carbon, but there are 2 pairs of valence electrons on oxygen. So let's calculate. So first let's take about the carbon. How many sigma bonds? 2 sigma bonds. You know, here we have a double bond, right? When a double bond is forming, one is sigma, the one is 5. You need to know that. So here in this carbon atom, sigma bonds we have only 2. Here 1 and 2. Is there any valence electron pairs? No, right? There are no valence electron pairs. None. So the total is 2. So find the hybridization of the carbon atom. It should be sp. And let's go for oxygen. Right? So here, if I take this oxygen, how many sigma bonds? Only 1 sigma bond, right? Only 1 sigma bond. Only 1 sigma bond. There are no any other sigma bonds. So sigma bonds, only 1. How many valence electrons? 1 and 2. Valence electron pairs are 2. So the total is 3, which have to be sp2. Here 2 and 1 equals to 3. We get it, right? So the 5 bonds here, 5 bonds, as I have told you before, they have no involvement in the hybridization. So you do not have to consider the 5 bonds when it comes to the hybridization. So let's take another example. Let me erase this. this is pretty easy, right? You just need a few examples to practice, and then it's pretty easy. So here we go. Let's take a little bit complicated one. Let's take nitrobenzene. Right, nitrobenzene. Or I will represent it like this: 1, 2, and 3. So I have been asked, what is the hybridization of this carbon and this carbon? So you have to have a very good clear idea, right? Even though we are not representing the hydrogen atoms over here, there is a hydrogen atom for each carbon in the aromatic ring. There cannot be a hydrogen on this carbon, right? As you can see, if there is being a hydrogen on this carbon is going to be much unstable because it contains 1, 2, 3, 4, 5 bonds. Carbon cannot take 5 bonds because carbon is on the second row. So carbon cannot take 8 bonds, which means this carbon doesn't contain any hydrogen. Okay, so let's go with this carbon. First thing, how many sigma bonds? 1, 2, and 3. Sigma bonds are 3. Any valence electrons? No, right? Any valence electron? No. There are no valence electrons. So total number should be 3. So find a suitable combination, which should be sp2. Here in this case the same, right? How many sigma bonds? It doesn't matter to what component this carbon has attached. No, we do not care about that. Or we only care about is how many sigma bonds. That's all. 1, 2, 1, 2, 3. There are only 3 sigma bonds, which means sp2. This is a double bond, right? So this bond should be a 5 bond. That's why we are not considering it. Okay, let's take another one last example. Let's take sulfate, right? So let's take sulfate here. This is the sulfate's Lewis structure. Okay, here I have drawn the sulfate's Lewis structure. Okay, now we have been asked what's the hybridization over here. Let's take it at A. And what's the hybridization over here? Let's take it as P. And what's the hybridization over here? Let's take at C. Okay, for A atom, how many sigma bonds? You can do it, right? How many sigma bonds? Only one sigma bond. How many valence electrons? 1 and 2. Total is 3. What should be the combination? Then it should be sp2. Here 2 and 1 equals to 3. Then it should be sp2. Let's take for B atom. Okay, here this one. How many sigma bonds? Only one sigma bond. How many valence electrons? 1, 2, 3. Valence electrons are 3. Total is 4. Then it should be sp3. Final one. So the C atom. How many sigma bonds? 1, 2, 3, 4. Sigma bonds are 4. Any valence electrons? No, right? No valence electron on sulfur. So 0. So the total is 4, which should be sp3 hybridization. So this is all about the hybridization. In next video, let's talk about the Vesper theory, which is more important to determine the structure or the geometry of a molecule.